Pareto 1, Pareto 2, and GPD, or shall we look at it like Pareto 3, Pareto 4, so.
Yeah, if you can find a few different Paretos, yeah, it'd be good. I mean, it will add on to what we've done already. Because I mean, there are so many different variations of Pareto. You know, I mean, there are many different generalizations of the Pareto in the literature. So if you can. Hi, good morning. If you can do all of it, then that'd be good. Yeah. Hi. All right, guys, good morning or good afternoon, depending on where you are. Not many people are here today, also in the Zoom. So yeah, just a reminder, if you haven't submitted quiz number 4, please do so before 11 a.m. UK time. As always, I will try to have all of them marked, which I do by myself, as you know, and return them to you later today. If not, I will return them to you tomorrow in the morning. It seems, yes, looking at it, it seems most of you have done well on this 4, but some have problems. Okay. All right. So in the 2 weeks before the reading week, I talked about portfolio theory. Today, I'm going to start on a new topic, which is called financial risk measures. I hope you guys looked at the videos. I think there are 4 or 5 videos I asked you to look at. I hope you did that during the reading week. So I just quickly run over the material without actually explaining anything. I'll just run over the 4 or 5 videos I asked you to look at. So the first video was about just the definitions. Now, what is a financial risk measure? Is usually a loss associated with an investment. Sorry, what is a financial risk? So it's usually a loss associated with the investment. And what is a financial risk measure? It can be like probabilities associated with the variable, like loss, right? Okay. Now, graphically speaking, a financial risk can be explained by these pictures, which I showed you in the videos. Like, so here is a businessman trying to cross the river from one end to another end with a lot of cash without being caught by the sharks. So this is another picture. I think I explained this in the video, right? So these are 3 pictures. I'm giving a graphical representation of what a financial risk is, right? So you need to make a calculated risk. Now, so this chapter is about financial risk measures. Now, a risk measure is usually, loosely speaking, is defined as a function that satisfies these properties: the normalized property, the translative property, and the monotonic property. So the first property says that the risk associated with 0 loss is 0, which makes sense. I mean, if you have 0 loss, right, then the risk also 0, right? Okay. So any measure that satisfies these properties is a risk measure. Then there's something called the coherent risk measure. A risk measure is said to be coherent. You know, the word coherent in English language, it usually means a good risk measure if it satisfies the 3 properties plus the 2 additional properties, which are called the positive homogeneity property and the subadditivity property. So this is the positive, C must be positive, and this is the subadditivity property. So if a measure satisfies these 5 properties, then it's said to be a coherent risk measure, right? Now, next thing, I'm going to talk about 2 most popular risk measures. The first one, okay, suppose X is a random variable representing loss. The most popular risk measure is known as the value at risk, or abbreviated as VAR, not variance, but VAR, V small a capital R, and is defined as the infimum of the set of all U for which the CDF of X is greater than or equal to P. So P is obviously a number between 0 and 1. Fx denotes the CDF of X. So this is one of the most popular risk measures. It was, I think it's due to JP Morgan, which is an American, I'm sure you know, American insurance company, right? Now, this looks complicated. If you are scared about mathematics, I mean, don't be worried about this. I will give you a simpler formula later on. Okay, and the second most popular risk measure is expected shortfall, and it's defined by this complicated formula, where the indicator function, I'm sure you know, the I denotes the indicator function, and it takes these 2 values. If you don't know what this is, you might have seen this before in other courses you have taken. So indicator function usually means it takes 2 values, 1 or 0, depending on 1 if the event in the brackets is true, 0 if the event in the brackets is a false event, right? Okay, and ES is it was due to these people in the 1990s. All right, I give an interpretation for both risk measures. Now, the next question, natural question to ask is whether these 2 risk measures, are they really coherent risk measures, yes or no? So that's what I have tried to address in this page. So as you can see, the VAR satisfies 4 of the 5 properties, but it doesn't satisfy subadditivity property, whereas the expected shortfall satisfies all 5 properties. So it is a coherent risk measure, whereas VAR is not a coherent risk measure, right? Okay. All right. And there are proofs. I mean, later on, I will talk about proofs for these facts that the VAR satisfies all but the last property, and the fact that the ES satisfies all 5 properties, right? Now, because of the fact that VAR has been one of the most popular risk measures and is not a coherent risk measure, after the 2008 crisis, you know, there was a big crisis, financial crisis in 2008. There were a lot of articles in the news and online blaming that the fact that the VAR was not a coherent risk measure might have led to the financial crisis of 2008. So these are some articles. I talked about this in the videos. I think I showed you some of this in the video. So it says VAR, the number that killed us, saying that VAR was to blame for the financial crisis of 2008. This is another article. Did VAR cause the crisis it meant to avert? This is another. This is another article which says, did VAR cause the crisis? It was same title. This is another one. VAR and its role in credit crisis. So these are some, I'm sure there are many other articles saying that the use of value at risk might have caused the financial crisis because it's not a coherent risk measure, right? I mean, you can read more about this use in the videos I sent to you. All right, in the next page, I'm going to talk like if the variable x, which represents loss, if it's absolutely continuous random variable, then you have these simple expressions for var and es, right? So this is the inverse CDF, and this is just the integral of the inverse CDF, right? And then I did some examples. This is the first example I did in the video. I hope you followed this. Do you have any issues with following the examples, guys? I mean, also the guys in Zoom, please let me know if you had issues with the examples. This is the second example I did in the video. This is the third example I did in the video. This involves integration by parts, right? And once again, if you have issues with the following the derivations, please let me know. Okay, now these are the proofs. Now, this is the proof that the var satisfies the normalized property. This is the proof that the var satisfies the translated property. In each of these proofs, as I'm assuming that x is a continuous, absolutely continuous random variable. I mean, more general proofs can be found online. And this is the proof that the var satisfies the monotonic property. And this is the proof that the var satisfies the positive homogeneity property. And for subadditive property, you can you should go to the course website. I'm sure. Sorry. Are the proofs examinable? Well, maybe they are examinable. Yeah, maybe they are. I mean, I can't be sure, but they may be examinable. Yeah. For the subadditivity property, there are. If you go to the course website, I given a link in the course website which gives proof that the subadditivity property does not hold for var. Okay, so please, you should go to the course website, you'll see the proof. Okay, all right. Now, these are the proofs for the ES, the expected shortfall. So there's a proof for normalized property, there's a proof for translated property, and this is the proof for monotonic property, positive homogeneity property. And again, for subadditivity property, again, you should go, the proof is on the course website. So you should go to the course website, you will see a link giving the proof for the subadditivity property of expected shortfall. All right, guys. Any questions? I'm sorry, I'm run through it quickly, but because these are stuff I already asked you to watch. So, any questions on what we've done so far? Veronica, you okay? You sure? No questions, Robert? Yeah. Okay. All right. In the rest of the time today, what I'm going to do is to do some examples on derivation of var and es for various distributions of x. Remember, x represents loss, right? So let's put this over here somewhere. All right, so let me start doing some examples. So some of these examples are trivial. I mean, so this is example 1. You see this issue comes. So suppose so I'm assuming throughout that x represents the loss. Right. Yeah. Okay, guys, so so in order to find the value at risk, all right, all you just, yes, you find the inverse function of the CDF, all right? So basically you set f of x to p and solve for x in terms of p. I'm sure you know that. So so this becomes this, and this becomes okay. So this is the value at risk for if x is assumed to have this CDF, which is trivial really. Right now, to find the expected shortfall, okay. All right, and if you do the integration for this, you get 1 over p t . So this is 1 over p times right, and this is equal to okay, so this is the formula for the expected shortfall for this example, right? You guys okay with this? Yeah. Yeah, right. Okay. The next example, I mean, there's no need to copy it down, but I will scan this stuff later on and put it online so you can see what I have written. Okay, so this is example 2. So suppose x okay. All right, guys, so oh, sorry. All right, so the first thing is to find the inverse CDF. So you set the CDF equal to P, right? Yeah. So this becomes 1 plus x over a is equal to 1 over p. So x, I'm doing it slowly, but and I hope, I mean, I can do it a lot faster, but I just want you to follow. Yeah. So x is equal to yeah. You okay, guys, so far? Yeah, let me know if you're not. So what we have is that the value at risk is given by this. Now to find the expected shortfall, yeah, you can write like this, and this you can write like yeah. Right, now I think this integral, I mean, it's not a standard integral, but I think I mentioned this before in one of the classes before, right? The CDF of a beta random variable, all of you know the beta distribution, which I assume you know. Yeah, its CDF involves what is known as the incomplete beta function, right? So let me write it down in case you forgot. The incomplete beta function is defined by the following. I don't know, some books may call this different. I don't know what the terminology is, but this is the term. I mean, the terminology may be different in different books, but this is the term that I normally use. It's just it's the version of the beta function. You know, remember the beta function, for the beta function, the integral goes from 0 to 1, whereas here the integral goes from 0 to a number x, which is less than 1, right? Okay, so that's why it's known as the incomplete beta function, right? And as I said, the CDF of a beta random variable involves the incomplete beta function, right? So using this definition, you can write this guy here as 1 over p times b p. Your alpha will be 1 minus 1 over a, and your beta will be 1 plus 1 over a. Right? You follow me? Yeah. Okay. You guys okay? Any questions on the Zoom, guys? No. Okay. All right. So that's example 2. Example 3, slightly more involved. Involves okay, guys. So this is known as the logistic distribution, the CDF of a logistics distribution. So x here, x goes from minus to plus infinity, right? Okay, so to find the inverse CDF, you just set this equal to P. So this is equal to this, yeah. So all right, so your x is gonna be minus log of 1 minus P divided by P, right? So your var is this, yeah. All right, guys, so now to find the expected shortfall, you use the formula, which is 0 to P log of 1 minus T divided by T dt. Now, how would you do is again this trick about using this how to do this integration? I think you should be familiar with this integral. How do you think we can do this? You have any ideas? Yeah. So you can do integration by parts to work this out. So you get this integral here. So you need to apply 2 times integration by parts 2 times, right? So if you apply integration by parts to this one, you get, correct me if I'm wrong, you get this 0 to P, and if you apply, then you get minus gives you plus 0 to P, T 1 minus T dt. Yeah, and if you apply integration by parts to this one, you get plus T divided by T dt. Okay, guys, let me know if I'm wrong. It's quite possible. Maybe wrong. Yeah, so now taking the limits at P, you get log of 1 minus P times P. At 0, you get 0. Now this guy here, you can write it as you can write it as T minus 1 plus 1. I will explain why I'm doing this in a minute, but you can write it like this. Yeah. And here you have, sorry, minus log of P times P plus 0. And the integral of 1 is 1, T, so you get P. All right. So what is left is just to do the integration for this, yeah. So what is left? Check my calculations, okay? So this is, you have log of 1 minus P times P. Now the integral of this is minus 1 over that, so it's gonna be minus T minus log of 1 minus T. Take the limits from 0 to P. All right, minus log of P times P. Am I right? Let me know if I made any mistakes. Yeah, so now finally taking the limits, you get log of 1 minus P times P. At 0 is 0, at P is minus P minus log of P times P. All right, this is what I'm getting. May not hopefully correct, but you can check. Yeah. Okay. All right, guys. Any questions so far? Anyone on the Zoom have questions? It's one more example I have. There's one more example I have here, which is slightly more involved. Is this okay with everybody or no? You have questions on this? Okay. All right, I'll take this away. Just one more example I have, which is more involved. So this is the last example I'm going to do today. So this is example 4. So here, suppose okay, so okay, all right. Now to find the value at risk, so you set this equal to P and solve for X. So this becomes X times 2 minus X. Okay, so this becomes 2X minus X squared minus this is 0. So X squared minus 2X plus this is 0, right? Now, this is what you have here is a quadratic equation, right? So there are two possible solutions. So X can be, I mean, you know the formula, right? Minus B, 2 plus or minus b squared, which is 4 for AC. AC is 4 times this divided by 2, right? So you can simplify this to 1 plus or minus 1 minus right. Now let me ask you, like, there are 2 roots here. Which of the solution, which of the roots or other, which of the roots is valid, and or do you think both roots are valid? Huh? Why is that? Yeah, okay, yeah, sure. So since x is between 0 and 1, the positive root cannot be valid, right? So what you have is that x is equal to 1 minus so the value of risk right. Okay, so that gives the formula for VAR. Now to find the formula for the expected shortfall, right, this is what you have, right? And there are 2 terms here. The integral of the first term is trivial, right? So you get 1 over p, p minus brackets all right, now to integrate the second term, to integrate the second term, you can do some substitution and see if it works, right? So what I'm going to do is I'm going to make the substitution that set y equal to this, right? And let's see if it works. I mean, we can try other substitutions too, but I'm just trying to figure out if it's going to work or not, right? So if this is the case, then t will be equal to y to the power a. dt by dy will be a times y to the power a minus 1, right? So let me put this in a box. Yeah. All right, now sorry. So putting this back into the integrand, this is what you will get. This is 1 over, well, this becomes 1 minus 1 over p. The limit, when t is equal to 0, y will be 0. When t is equal to p, y will be this, okay? So this becomes this. And dt is 8 times y to the power a minus 1 dy. You follow me, right? Okay. Okay, now a is a constant, so you can pull it outside. So this becomes 1 minus a over p times the integral from 0 to right? Now, this integral should be familiar to you. Remember the example that I just did. You remember this example where I used the incomplete beta function defined as this, right? So because what you have here is also an incomplete beta function, right? Right, you have y to the power m minus 1 times this. So this you can write as 1 minus a, your alpha is a, and your beta will be 3/2, right? Okay, so this gives the formula for the expected shortfall for the last example. And by the way, if you are familiar with R, I assume that all of you are familiar with R, right? There are functions in R for computing the incomplete beta function, right? So it's not something, you don't need to write your own code. You can just use the function in R, computing that. Yeah. Okay. So these are, for example, so any questions you guys have, please let me know. I want to show you something before. Don't know if I can. You can see this, but. I want to show you something before we call it a day. All right, so this is the course website, as you know. So if you go here, there are, all right, this is the proof. This is the one I mentioned earlier. So if you go to this link here, it gives the proof that, this is the proof that the var is not subadditive, right? This is the proof I mentioned that. Oh, by the way, can the people in Zoom, can you see me? Share screen. Okay. This is the proof that the value address is not subadditive, right? And this document here gives 7 different proofs that this expected shortfall is subadditive, right? So you should go through it. I mean, I don't expect you to know this proof. Some of these are complicated, I think, for your level, but you know, but it gives 7 different proofs that, you know, it gives 7 different proofs that the expected shortfall is subadditive, right? And another document I like to show you is, I hope it is here, just a minute. Oh yeah, this, you should look at this link here. You should go to this link, right? It gives, this table here is pretty extensive. It gives the formula for, I don't know if you can see this, but yeah. It gives the formula for var and expected shortfall for nearly over 100 distributions. So you should go through this link. It's about 12 pages. It's 12 pages long. I think it contains over 100 distributions. And for each distribution, it gives the formula for var and ES. Okay. So this is something that was done by some of my PhD students some years ago. Yeah, so some of these formulas are really complicated, but as you can see. Okay. All right, so so these are 3 links I wanted to show you. So the last, sorry, these 2 links here give the proofs about subadditivity, and the link here gives the formulas for var and es for over 100 distributions, right? All right, guys, so I will see you guys on Friday. As you know, there's a tutorial on Friday on from 12 to 1 p.m. Yeah, and so if you have time, please go through the easy questions, right? I think all of them are easy. So try to go through as many as you can, and I will see you on Friday, guys. Yeah. All right, guys, take care. Yeah, bye. So Robert, I will see you around 4 o'clock.
Your office.
Yeah. I'll be in my office. Yeah.